Hi, good morning and welcome to the ZP Developer Zone. So every Thursday at 8 a.m. London time, we like to do a webinar for the members of our ZP Developer Zone, and we like to answer questions that have come in for the week. So I always say this, I'll have to talk fast because there's essentially a lot to get through. So I'll put the slide up and quickly just say that at Zimmer & Peacock we do try to provide a lot of resources, many of which are free. So I will refer to the ZP Academy probably on the next slide, so I won't mention it now. We do this webinar every Thursday at 8 a.m. and so, if we have technical questions and we feel like, that we need to provide, let's say, a free answer to it, then we can use the webinar format as we do. ZP does have collaborations. Collaborations really often mean with universities, but we do have many of them with universities. I think for a company of our size, we have a very large number of PhDs, for example, under sponsorship. Through the social media, we do offer, talk about many jobs that we have, and of course we have the ZP Developer Zone website. As I say, let me jump into it. And also we do organize workshops. For example, we have a workshop not this Sunday but next Sunday in Spain in a town called Sigues. El Sevilla have a biosensor conference, and we're doing a workshop at 2 p.m. there. So we do workshops as well. First of all, I just want to highlight the ZP Academy, that there is the ZP Academy and there are 2 free courses on it. The reason being is I will, at least today, mention differential pulse voltammetry, cyclic voltammetry, and chronoamperometry. And so and also impedance spectroscopy, so if these terms are not super familiar to you, then it's probably worth taking a look at the ZP Academy. Anyway, that said, let's go forward. So this week we've had 5 questions. Question number 1 was, somebody was really just inquiring about gold electrodes. And whenever somebody inquires about gold electrodes, I kind of assume that they're actually making some sort of immunosensor. And we're going to talk about gold versus carbon. In the past, I would have suggested gold and carbon were somewhat equivalent when it came to manufacturing electrodes and sensors. But I think that I had to change the thinking on that a bit because the price of gold is going so high, and I really don't think it's actually going to come down. I mean, this is just an anecdote, but we had to purchase some gold the other day, and we ended up spending 50,000 euros on gold. Whereas if the same amount in carbon would have been, less than 1/10 of that, let's say. So be careful when choosing to use gold, even in an R&D setting, because if you develop your whole assay upon gold, it might be very hard to roll back later on, and it will make it more and more expensive to actually commercialialize that. We also had another question about arsenic, the detection of arsenic in water, and so we will address that. We also had a question about the detection of alcohol in water, and we will discuss that. We had a couple of questions come in yesterday. One of them was about electrodes in microfluidics, and we'll talk about that. And lastly, about electrodes for educational purposes. I just want to say hi to Prasad. So electrodes for educational purposes, and I will also discuss that. So there's 5 questions. We try to get this done within the 30 minutes, so I should really go forward. The reason that people often ask us, and we did have a question about this, gold electrodes, is because they're really trying to make a sort of immunotype sensor where they've coupled, often using what we call a thiol linker. They've coupled an antibody, for example, more and more often now. Single strand of DNA is also being done because people are going towards molecular assays as well, but they've coupled some sort of macromolecule. In this case, I've shown a sort of antibody coupled to a gold surface. This is why people ask us about gold electrodes. Now, I'll recommend a gold electrode, no problems, but I'd also recommend that actually people started to think about using carbon instead of gold. And it's really just based on cost, I would say. Now, if people are talking about performance, people try to suggest that graphene is better than carbon. I'm not sure if that's really the case, but I also want to show that even a graphene electrode from Zimmer Peacock can be lower cost than a gold electrode from Zimmer Peacock. The reason being is with graphene, the raw material itself, is actually low cost. The processing adds more cost to it, but the raw material itself is low cost. Whereas with gold, the raw material itself is expensive, and then the processing just adds more and more expense on top of it. So let me go forward a little bit, and anyone who's watching live, if there's any audio quality issues, let me know so that I can address them. But we get asked, for a gold electrode, it's often the case that people are asking for gold electrodes because they're thinking about immunosensors, and I would actually suggest, and I'm going to sort of go through it a little bit now, why carbon I think is a better choice than gold, and I would actually suggest that people start going in a direction of gold. Of carbon. Any links that I put in these slides, I'll also put them under the video afterwards. So the other thing I would say as well is, if you're using gold because it's particularly active towards a molecule of interest, so for example, hydrogen peroxide can be oxidized on gold, whereas it's very poorly oxidized on carbon. So there are situations where you sort of think, no, I definitely have to use gold. It's not because I want to link a molecule to it, it's because I need that gold catalytic surface. In those cases, there are still alternatives, and I would be suggesting that you use a mediated carbon. Again, these electrodes from Zimmer Peacock are lower cost than the gold, and because they're mediated, for example, the Prussian blue, you can detect hydrogen peroxide as well. So I've sort of said it several times now, but people come to us, they say, I want a gold electrode. That's completely fine. I suspect whenever you ask for gold, it's really because you're trying to do some sort of, I call them immunosensors, where you're putting a macromolecule onto the surface of the gold that's specific. You can definitely do that with carbon. If you want the gold because of actually some sort of electrocatalytic properties, then I would say that you can also use mediated carbon, and again, these are lower cost than the gold. It's gold itself that's the issue at the moment. So to turn a gold electrode into an immunosensor, it's fairly straightforward. We use this sort of this kind of thiol linker. It's got a thiol group at one end which just loves to attach to gold, and a carboxylic acid at the other end, which we can couple to. We can then couple or activate it first of all using a reagent system called EDC NHS, and then once we've activated the carboxylic acid, you can then add your antibody, and your antibody's kind of on the surface. The last step really then is to block the gold. Bovine serum albumin, for example, is commonly used. So again, when I'm asked, oh, do you have gold electrodes? It's really because people are asking, often, let's say 90% of the time, because they actually want to do a immunotype sensor or build a sensor using what we're showing here. They put a thiol linker on there, they activate the thiol linker, they add their amine, they might end up blocking the gold, but they're really all following this kind of step, and it's all following the same workflow. And we do this ourselves, so this is a good example where we've taken one of our gold value electrodes, and we've made an immunotype sensor on top of it with an antibody, and then we've tested it by, in this case, EIS, electrochemical impedance spectroscopy, and we test it, and we can see that our signal is developing as a function of concentration. So using Zimmer and Peacock value gold electrodes works perfectly well, and we know because we do it ourselves. I've said this in the past, but the biggest consumer of ZP screen printed electrodes, it's a very unusual business model, is actually Zimmer and Peacock. That we do, we use our own materials in client programs to develop their assays upon. So in answer to the specific question, can ZP recommend a gold electrode? Yes, we can. I suspect that the inquiry is using wants to do an immunoassay. Yes, you can do this, and we do it ourselves. But my actual suggestion is don't necessarily just jump into gold. I'd actually suggest you try carbon. This is a paper that I often cite. There's a couple of ZP guys on this paper, myself and Sindra, and a couple of good friends of the company as well, Samar and Shaquille, are on this paper. And in this paper, what we're doing is we're taking a carbon electrode and we are activating it with a reagent called pyrene NHS. So the pyrene, in the previous gold activation, we will sort of say there's a thiol group that binds to gold. I would, in this particular way of making a biosensor, it's this pyrene group, which is really a 4 aromatic rings. They stack on top of the carbon really well. And this reagent in some ways is simpler because it actually comes with the NHS group on it already, so it's already activated to be able to couple to the antibody. So you don't need to go gold, thiol, activate the thiol, then put the, let's say, antibody on it. In fact, you could just do it this way. There's too much echo in the background. I'm so sorry, I didn't realise there was so much echo in the background. Oh, that's such a shame. I'm just getting a comment online that there might be too much echo in the background, so I will have to fix that, and I apologise for that. Yeah, I hear what you're telling me. There's too much echo in the background. I'm so sorry, I didn't realise there was so much echo. I'm trying to see if I can fix that now. I'm just getting a comment. Right, so I'm hopefully I really didn't realise there was echo in the background, and I apologise for that sound quality. Yeah, I hear what you're telling me there. Yeah, so I think I've actually fixed it now, but apologies for that. But thank you for the feedback from Hasim. Hasim, give me some feedback if the echo's gone. Right, so back to the point anyway. You can replace gold with carbon, and this pyrene molecule could be a good way of doing it. But thank you for the feedback. Right, and I think it's simpler. Now in this paper we do show how to make these types of sensors, so I'll just go back to the paper and say, take a look at this paper. It is actually free, this paper, to look at, so should be no issues in following it. And it does work as well. In this particular paper we followed the assay by DPV, differential pulse photometry, DPV. It was unusual because we often use a blocking assay format, where you expect the signal to decrease with the amount of antigen in this case, but actually the signal went upwards. We explained in the paper we thought it was electrostatic, but you know, you can always come up with a theory. Of course, you know, am I 100% convinced? I'm probably convinced, but I haven't fundamentally proven it. But the signal was actually going up, or the magnitude of this signal goes up with the amount of binding, which is kind of really nice. It's probably worth saying that when we do an immuno type sensor, whether it be on gold or carbon, we put about 111 hours worth of effort into this, so it's not quick to get hold of some screw pins or electrodes and to get some sort of calibration curve. Even this calibration curve is far from perfect, let's say, but you know, it was proof that we were getting something to work, but you have to put quite a few hours into it. So in summary, if somebody wants a gold electrode from ZP, then I suggest our gold 303. It's in the value section, but I would generally suggest that they actually tried out one of our carbon electrodes, and as I say, any kind of yeah, and really I would suggest gold, and I would really suggest that actually they should really go for the carbon. Now the next question in the line was detection of arsenic in water. With this detection of arsenic in water, the first thing is I just took a quick look in the literature, and you know, I always feel like the nice thing about electrochemistry is that there's always plenty of papers regarding you know, electrochemical detection. So in that paper they talked about using this is very important, that they used a glassy carbon electrode to detect the arsenic, and they activated the glassy carbon using something called crystal violet, and they probably activated, well not, they did activate using cyclophotometry, and then they detected the sensor using arsenic, and they got a quite a nice linear signal. I like this paper because in some ways, A, it works, B, they're working on carbon, and C, I think it's actually quite simple what they've done. Now, what I would say is this, that I really recommend that people don't use glassy carbon electrodes in their R&D. The problem with it is you can get nice results and nice papers, but it doesn't really explain or show anyone how you could actually use this in, let's say, in the real world. If you want to detect arsenic in water, then you're often talking about, testing, trying to do low-cost testing in, potentially in rural environments. There might be a local well, they might be pumping from deep underground, there might be arsenics in the water, and they might have to be testing. So I know there's parts of the world where they are doing this kind of deep well pumping, they're concerned about arsenic in the water, and, glassy carbon electrodes sort of suggests research, it doesn't suggest a in-field low-cost test. So I would definitely suggest using screen printed electrodes. So in this, I would almost, if I was to make an arsenic sensor, I'd almost follow this paper, but I would make an important change. I'd either be trying our hypervalue screen printed electrodes, a sheet of these hypervalue electrodes. I realize the guys have reviewed the pricing, and they've actually now made a sheet of 300 screen printed electrodes, 145 euros. So this is less than 50 cents each, and that's, I consider, quite low volume. So it's definitely worth trying out these hypervalue electrodes, and you can also try out these graphene electrodes as well. Now they're more expensive. They're 200 for 390 euros. It's because there's extra processing when you're trying to do graphene. So I would suggest trying both, but I would hope that you could get away with actually just the normal carbon electrodes. So I would say this, that you can detect arsenic in water, and I think the paper that I showed previously is actually a good starting point for it. But you have to make a very important point, a change. Don't use the glassy carbon electrodes. They've done it already on glassy carbon electrodes. That's great. They've proven the principle. But to really add some value and to make it more of a product, then you should really be starting to get it onto hopefully carbon electrodes. But it's also worth having a look at the graphene electrodes as well, just to see if it helps with the limit of detection, for example. And you will need a connector as well, because I don't know the inquirer what kind of potentiostat he has, but the kind of connector I'm showing here allows you to plug in sort of 3mm banana plugs, like the kind that come on palm sense or come on Anapot as well. So I suppose the arsenic is actually interesting to anyone who's really interested in doing water testing. Which also now brings me on to detecting alcohol in water. So at ZP we have an alcohol sensor, and many of our sensors look the same. This sensor, as it looks today in that picture, is actually good for, I would say, sort of in laboratory testing, in vitro testing. If people want to put these sensors into the environment, then we have to have a different conversation. But you can take, our sensors, I'll show you how we do the experiment in a minute, but we test them, we test them at 2% alcohol, by volume. So we get a jump in signal. So I have a baseline signal, then I get a jump in signal, then we increase it to 4%, we get an increase in signal, then 5%, and we get an increase in signal. So at Zimmer and Peacock, and then we've plotted signal versus concentration, and that gives us essentially our sensitivity. Now, how we got that kind of data, it's important to understand that that's very much a laboratory experiment. And I've shown this kind of slide before, but we often do our experiments when in the laboratory like this. We'll take the sensor, we'll invert it into a solution, we'll put it on a magnetic stirrer, we'll use chronoamperometry. So it's important to say that, and if you're not sure what chronoamperometry is, then please look at the ZP Academy. The 2 courses I suggest are free. So we get first of all, we let the sensors break in, we call it, and then we add, let's say, a drop of alcohol. This would be a sort of concentrated drop, and it will get dispersed because of the stirring into the solution, and we then get the signal rise. And when we think the signal's plateau, then we'll add the next drop. So that's how we kind of prove out an application. Now, the sensors that we have on the website allow people to kind of get quickly going with our technology. We can also prove our applications at Zimmer and Peacock. We call that kind of proof of principle. But I have a feeling that often when people are coming from industry, they're looking not so much for laboratory experiments, but they want real world data. They need something that's more robust. So first of all, I just want to kind of say that if you want to see how we do our laboratory experiments, we have something called the application zone. There's plenty of videos up there. These videos are almost in chronological order, so you'll notice that the quality gets better over the years as we become, at Zimmer and Peacock, let's say, more sophisticated. So it's probably worth taking a look at the videos, especially the last 3 videos, and we often do that kind of beaker testing that I've just described. Now, we've been asked, can you detect alcohol in water? Yes, we have a sensor for it. The data that you see on the web store, I'm now describing how we've gathered that data. If you need to be detecting alcohol in water in a continuous manner or in a robust manner, I just want to show you something that we have. This is our rod technology. If you zoom in on this rod technology, you can see that we have the sensors in position here, and that's the sensing element, let's say. And then the rod itself actually looks like this. We have electronics at the top of it. We have the sensors, and in this case, this sensor is actually this rod is put into soil. So we were measuring nutrients in soil. We bury it, and then the sensors were at a depth of 30 and 60 centimeters into the soil. Now, the way this electronics works is this: that we have our rods. Our rods have telemetry on them. We will send the data to what we call a base station, and then using, for example, either LoraWAN or a local Wi-Fi connection, we send the data to Julie. So I bring this up because I feel like the inquirer is actually much more industry focused. They might even want to be doing continuous measurement, but they probably want to do measurement in a robust manner rather than a laboratory experiment. So the sensors we have on the website, the data comes from laboratory experiments. If you want to make the technology more robust, then you probably have to have us put it into this kind of rod format. And we have a sort of stack of technology where we can put the sensors into the application. We have wireless that sends it to a base station. Base station sends it to a proprietary database called Julie, and then from Julie we can send it to we've been doing it for apps that we've developed, or you can also get the data out using an API as well. So I just kind of bring that up as well. Mohammed's just asking if the nitrate sensor is for sale, and the quick answer is the nitrate sensing technology we have on our ZP Ag website. We actually do have a starter kit up for sale there. And we're mostly and we are selling that at the moment. We're also using the stack of technologies of the rod, the electronics, the Julie, also then for other applications as well. I feel like this measuring alcohol in water is one of those kind of applications. Now, and so we sort of imagine in this case, these sensors will actually be within a solution because we're trying to measure alcohol in water. So I'm looking at the time. Okay, we've got some time. Now the last question, what they're asking is, can we put a carbon electrode of 50 micrometers, so 50 micrometers is half a human hair's width, into a microfluidic device? I'll sort of partly answer the question and say this, that I think the screen printed electrodes are a good format for building microfluidic devices on them. I like the fact that the hypervalue electrode, we were sort of showing it earlier on, and the graphene electrode, they're 50 cents each or less than 50 cents each. So it really gives you a platform on which you can break a few or break a lot, and it definitely won't break the R&D budget. What I suggest is that you take one of our hypervalue electrodes, for example. We've done this in the past where we've actually, I don't know how the inquirer wants to make his microfluidic device. We've 3D printed, but of course I understand this gentleman might want to be making a much finer channel than that. So, but what I said, because obviously you might not have the resolution on a 3D printer, but what you need to do is create essentially a structure on top of our hypervalue electrodes. I don't know if you're going to use PDMS or you're going to do 3D printing or laminating. It's kind of up to you. But in that device then you have a channel, and of course I understand you're trying to make a 50 micron, potentially a 50 micron channel, but essentially all you need to do is run the channel over our reference, our working and our counter, and that will work perfectly well. So I'm sort of saying to you, take one of the hypervalue electrodes, put your structure on top of it, and then only the part where the channel runs is essentially in the circuit. So when I look at that, I think it's not too difficult to make a channel that's 1 millimeter wide. I know that's not what you're asking for, but that's not too hard. And so then you could actually make essentially a very small electrode by just, the rest of the electrodes are all blocked by the material. But in fact, where the channel runs is where the electrode is exposed, and that will end up putting an electrode in a microfluidic channel. Question number 5. The question number 5 is coming from this situation that in academia, especially in teaching, people are very interested in generating cyclovoltammetry where they have something like a peak-to-peak separation of about 59 millivolts. So for a 1 electron transfer, if everything is, let's say, ideal, then the separation between the oxidation and reduction wave is about 59 millivolts. Now in this case, the separation is about 75 millivolts. So you can probably get perfection. You can get perfection. Now for Zimmer Peacock, we're a very practical company. We understand that having 59 millivolts peak-to-peak separation doesn't make the assay or the biosensor any better. It really doesn't add anything. But we do understand from a teaching perspective, this is sometimes required just to demonstrate to the students that the underlying maths is pretty good. So ZP, we do a educational sensor now, where we do have close to ideal behavior in terms of the peak-to-peak separation. So the lower the scan rate, essentially the closer the peak-to-peak separation comes in terms of idealness, and the peak height is proportional to the square root of, in this case, scan rate, and we're using ferrocyanide, so it tells us that we're under diffusion control. So in a teaching lab, we have now come up with an electrode which we kind of call the hypervalue educational electrode. It's a little bit more pricey than our standard hypervalue electrode, and that's because it's got some extra processing on it so that we can essentially reach the expectations of a teaching laboratory, so we've activated the electrode accordingly. But people can sort of buy this, use it as it is, and get some, and they should be able to get results similar to ours. So question number 5 is, do you have electrodes that sort of give ideal electrochemical behavior? And the quick answer is we do. We have these hypervalue educational electrodes. There's a bit more of a premium on them because of the extra work in developing them, but we do have them. Alright, and now I look at the time. It's 8:28 here in London, and I'll just run through the questions. So my apologies for the echo earlier on the line, and thank you for FTAB for catching that and letting me rectify it for the second half of this. If you're looking for a gold electrode, I generally, and you're making an immunoassay type sensor, I would definitely recommend going for carbon. Detection of arsenic, I really think you could actually do that. There's a good paper out there. It's quite simple. They use glassy carbon electrode. I would generally try using the screen printed carbon electrodes. Detection of alcohol in water, yeah, we have an alcohol sensor, and we have the data online, and I hope that's enough to sort of move people along. Electrodes in microfluidics, I would actually suggest you get a hypervalue electrode and make your microfluidic channel or chamber on top of that electrode. Don't try to put the electrode into the chamber, build the chamber on top of the electrode. And number 5, we do have now a series of educational electrodes. There's no need to activate these. The students can just use them as they come, and then essentially get a signal where the peak to peak is around about 75 millivolts, and they'll be able to do the signal versus scan rate or the peak versus scan rate and show that it's probably proportional to the square root of the scan rate. Okay, So that was a lot there. Thanks again to FTAB for catching the echo. I appreciate it. If you've got any questions, reach out to us. If you would like private consultation, that's one thing, and if you would like, not to, then we use the webinar